I know you all have been ready and waiting for this. It's the work conversation, and we're talking about the physics work, not the whack, 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 whack. And whoever wants to rewrite that song, I cannot wait to record it for you and post it online. So feel free, go ahead. That said, work, physics work, is defined as the force times the distance. So here we go. Get it all set up. Make sure we can read it. Not see the coffee maker. Very important part of my life. So, the work is the force times the distance. It's very important that the force is in the direction of the motion. So if you are not moving in the direction of the distance, you are not doing work. There's a lot of examples, and we will go over them. So 1 joule of work is a Newton times a meter. Okay, so if you did not read this part, go back and take a peeky-poo. It is 1 joule is equal to 1 Newton, which is the unit of force, times 1 meter, which is the unit of distance. And that is called a Newton meter. They have renamed Newton meter to joule, just for making it more easy for you. Okay. Here is an example. How much work is done when you have 10 newtons that's lifted 5 meters off the ground. Now keep in mind, if you were to draw the free body diagram, you are applying a force up of 10 newtons, and it is going to cover 5 meters. So that means that the direction of the force is in the same direction as the distance covered, which means that yes, work is done. So that's what you always need to make sure you check for. Are you moving in the direction of the force? If you're not doing work. So here we have work, which means that this is not a trick question. So what we do is we take our 10 newtons, which is our force, and we multiply it by 5 meters, which is our distance. The amount of work that we did is 50 newtons times meters, 50 Newton meters. And that can also be said as 50 joules. Okay? Remember, work is one of 2 ways that energy can be transformed. The other way is by heat transferring, and we know that is from hot to cold. Okay? So here we go. Let's do this. In your own words, define work in the scientific terms. If we want to do work, we must apply a force and move an object in the direction of the force. We have to move the object a distance in the direction of a force. We need to call and make sure that gets recorded on the song. How are work, force, and distance related? Work is the force applied to move an object a distance, and in parentheses, the same direction as the force. Okay. What are 2 different units? Remember, units are the things that go after the numbers. Here's a unit, here's a unit. They tell us what the number means. So up here we said that we have joules and Newton meters. So we can say we have a joule of work, or we have a Newton times a meter of work. For the following situations, is work being done? Right, work done or no work done for each situation. Now remember, we're going in the same direction as the force. Okay, an ice skater glides for 2 meters across the ice. So if we draw the free body diagram for an ice skater who's gliding, that means that they have gravity acting down, the normal force of the ice not collapsing underneath them, hopefully. And then we have no other force because it's just gliding. All right, but the direction of motion is this way, and that is our velocity vector. So that means that we have no force being applied in the direction of motion, so we have no work. Okay? The ice skater's partner lifts her up, which means that we have gravity, Fg, acting down, and then the ice skater's partner is going to be Fn plus and applied. And the direction of motion is going to be up. If direction of motion and the force applied is the same, we have work. All right, so for part B, we have work being done. The ice skater partner carries her across the ice, a distance of 3 meters. So now we have Fg, the gravity pulling down, F of the partner pushing up, but the direction of motion, our velocity, is across the ice. That means no work, because our velocity and our force are not in the same direction. After setting her down, the ice skater's partner pulls her across the ice, a distance of 10 meters. So now we have gravity down, we have normal force up because the ice is not breaking, we hope, and we have the partner applying a force this way. This is F partner. The direction of motion is that way, which means that this and the direction of motion are the same. So again, we have work. After skating practice, the ice skater lifts her 20 Newton gym bag up a half a meter. So again, we have gravity, Fg, acting down, and then she lifts it this way, F skater, and the direction that it moves is also up. So because these two are the same, again, we get work, 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 because the direction of motion is the same as the force applied. I don't know that I'm going to like this song for very long. Okay? Great job. Let's go to calculations, shall we? Let's get on up here. We've got a woman. She has a 100 Newton child. Whenever you see newtons, you know that is a force. She's moving up 1 meter. Be careful when they write out the words 1. So that is a distance, and carries her for 50 meters. So there's another distance to the child's bedroom. How much work does she do? Let's draw the free body diagram. Look at that child. Looks just like a box, as it should. Gravity acts down. The woman pushes up to lift her. The direction she goes is up. So here we have work done. When she starts to go this way for 50 meters, that is not work because it's not in the same direction that she's applying the force. And we'll call that F applied. Okay? So now the only thing that we can count in work is how much force, which is 100 newtons to counteract Fg, is going to move her in the same direction as the force, okay? Which was only 1 meter. So work is equal to force times distance, but the distance we need to use is the one in the same direction. So we have 100 newtons times 1 meter is equal to 100 Newton meters which is also 100 joules. So the only work she did was 100 joules. It had nothing to do with this 50 meters because that was not in the direction that she applied the force. Please be careful. Number 6. How much work, we know work is equal to force times distance, in the direction of motion, does another mother do if she lifts each of her twins, God bless her, up 1 meter? Those babies weigh 90 newtons each. Okay, so there's 2 of them, which means that she's doing twice the work when she lifts them. God bless her. So now we take our force, 90 newtons. Wait, is it in the same direction? Yes, because we have lifting, she is not carrying. Lift is work. Carry is not work. That's me putting a big circle around that work, okay? Carrying is not work. 90 newtons times 1 meter. This is 90 times 2. 2 times 9 is 18. So we have 180 newton meters, which is the same as 180 joules. Okay? Great. Now, you're sledding in all the snow we had this year. Ha 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 ha. We're going to pull it a distance of 500 meters with a force of 200 newtons. So when we draw the free body diagram, gravity acting down, Fg, we have the normal force of the ground not breaking, not making it float. So this is all balanced. Now we're going to pull our sled this direction with 200 newtons. That's called an applied force. That's 200 newtons. The direction that we're moving is also in this direction, which means that we are doing work. Which means that now we can say it is equal to the force times the distance. So we have a force of 200 newtons. We have a distance of 500 meters. When we drop off those zeros and we say 2 times 5 is equal to 10, and then we write all of the rest of our zeros. 1, 2, 3, 4. We have 2 more zeros, 4 more zeros. Let's just check to make sure that we do math right. Okay, so 200 times 500 is equal to 100,000. That's exactly what we got. Great. I can do math. You notice we have newtons times a meter, which is the same as 100,000 joules. Both of those answers are correct. Okay? Great job. Because the snow suddenly got too slushy, you decide to carry, there's the carry word, your 100 Newton sled the rest of the way. How much work do you do when you pick up the sled and lift it 0.5 meters up? How much work do you do when you carry the sled 800 meters? So there's 2 questions here. Be careful. First, let's answer this one. How much work do we do when we pick up the sled half a meter? We know that work is equal to force times distance. Let's draw this free body diagram. Here is the sled. Gravity acts down, Fg. We pick it up. This is us. F applied, and it is equal to, how much does it, 100 newtons. Okay, so if we pick it up, it's also going in the same direction, which means we again have work. So our work done is our force, 100 newtons, because that's how much it can make, that's how much we have to use in order to lift it, and we're lifting it half a meter. Now, half of 100, most of us know, is 50. But be careful and just put it into your calculator if you don't feel confident. 100 times 0.5 is 50. Okay? So we do 50 newtons times meters, joules of work there. Now, great. So we answered this question. Check. How much work do we do when we carry the sled? Let's draw the free body diagram again. We have Fg, which is the weight of the sled. That's actually 100 newtons. We have to pick it up and lift it. We have to support it at half a meter off the ground with 100 newtons of force. However, our distance is going this way, which means these are not in the same direction. So there is no work being done when we carry it home. None at all. We only do 50 joules of work to pick it up. Don't get tricked and answer both questions. Number 9, an ant sits on the back of a mouse, which would be weird. The mouse is still carrying the ant across the floor 10 meters. That's a distance. Was there work done by the mouse? Again, our free body diagram. Here's the ant's Fg, our weight. Here's the mouse making sure that the ant doesn't break through its back. But that silly mouse is carrying the ant this direction. You notice this is the direction of movement and this is the direction he's supporting it. So again, no work. Why? Because it's not in the same direction as the motion. Okay? You decide to add up all the work you did yesterday. You would be very ambitious if you did that. If you did 10,000 Newton meters of work, again, very carefully, reading, we know this is W, how much work did you do in units of joules? I'm not even going to grace you with an explanation. If you can't do this, you need to go back and read the first part first. Read it over and learn what a Newton meter is and how it relates to joules. Thanks. Last one. If you did 150 joules of work, which is great, it tells you this is work, lifting a 100 Newton backpack, which is the force, how high? So what's your distance? High is distance. Don't forget that. Did you lift the backpack? Did you lift it? Or did you do work? First of all, let's check. We have Fg, and then you lifted it, and it moved up, which means that yes, there is work. So we can calculate work. Great. But we don't need work because we've already been giving it. If we want to find how high, that's the distance. Work is equal to the force times the distance. So we put that into our cheat. We want to know how high, which is the distance. Let's get rid of that. The distance is equal to work divided by force. We look here, we have work and we have force. Perfect. We can figure this out easy. 150 joules divided by 120 newtons is equal to 1.25. Now if you know that joules is a Newton meter and you divide that by a Newton, you see that you are left with meters. Which makes sense because you were asked for a distance, which is measured in meters. Great job. Don't worry about changing it into pounds. It's a useless thing to do. Nice work, kids. Let's do the next one.